This meeting is being recorded.
In this next section, we're going to take a look at now carbon-13 NMR spectroscopy and some of the similarities and differences between that and proton NMR. So looking at proton NMR, we know that hydrogen with a mass of 1 is the most abundant isotope of hydrogen. So generally, we can see strong signals produced with proton NMR. But when we look at the active isotope of carbon, carbon-13, this is only about 1% of all carbon atoms that naturally occur. So we need a more sensitive receiver coil and, if possible, a concentrated sample or one or the other is definitely required with carbon NMR spectroscopy. So we also see some key differences with proton NMR. We look at the number of signals produced and then the shift, the multiplicity, the splitting that occurs, and the integration of the proton NMR signals. But when we talk about carbon-13 NMR, we only look at the number of signals and their chemical shift. So we don't consider the integration or splitting. So let's take a look at why. So generally, when we acquire this carbon-13 spectrum, we use this process of decoupling. So a broadband decoupled carbon NMR spectrum is generally what is produced and analyzed. For one, we don't really see coupling between two carbon-13 atoms because they are so rare, only 1%, as we mentioned. So the likelihood of two carbon atoms being carbon-13 isotopes and being within proximity of each other, that is rare. So we won't see coupling there. And then when we have proton H1 carbon-13 coupling, we see splitting that can be so complex, the spectrum would be unreadable. So what happens is they do this process of decoupling where they use two different radio frequency transmitters, one that only activates and produces signals for carbon-13, and then another radio frequency that produces all proton and carbon signals, and then that is they're able to subtract one from the other to decouple this data, and then we only see these carbon-13 spectra with all of the signals that result as singlets due to this process. So it makes a much easier to read spectrum. So let's take a look at this next section here. So section 12, the chemical shifts that are produced with carbon-13 NMR spectroscopy are very different frequencies. And that's because it requires different frequencies or energy to excite and resonate carbon atoms compared to our protons. And also this frequency then is going to be produced at a different shift or different range from our TMS standard. So we can still use this TMS as a standard with our carbon-13 NMR spectroscopy, and these signals will appear as a shift between 0 and 220 ppm. And again, each signal represents a unique type of carbon, as we saw with each type of signal that's presented in a proton NMR, the same thing as applied here. And as we saw previously, some hydrogens would be in the same electronic environment, the same chemical environment. We see that again with both planes and axes of symmetry in atoms, and therefore we see a reduced number of signals. than there are carbon atoms when we have these electronic environments. So again, there are a lot of similarities and a lot of differences, but the number of signals, again, is affected by the number of distinct carbon-13 atoms in each compound. So let's take a look at this first compound here, and we know that somewhere within the amount of molecules that we have, 1% will have any of these carbon atoms producing a signal. So in this first molecule, we see 4 signals would be produced. And then we see that one plane of symmetry. So you can see that on the other side, the right side of the molecule, those atoms are not highlighted because they would produce a symmetrical signal. So we have 4 chemically equivalent carbons in our first molecule. Then there are 5 chemically equivalent carbons seen in our second molecule. We would have 5 signals now. And we still only have that one plane of symmetry. Then we can see only 3 signals produced in this last compound, and that's because we now have 2 planes of symmetry. So count here, 1, 2, 3 distinct carbons, and then see how they are reflected either across the horizontal or the vertical plane of symmetry. So we'll continue with the last section on this depth NMR, carbon NMR spectroscopy in the last video in this chapter.